Hello and welcome back to BME 2315. In this lecture, we're going to be looking at a few additional topics that are relevant to Gaussian elimination. So to remind you, Gaussian elimination is a method to solve for x in the system ax equals b. And Gaussian elimination involves a forward elimination step where we're trying to eliminate the values in this lower triangle and make them all zero. In this particular example, because n is 3, we are going to do 2 rounds of forward elimination. The second row is showing what happens after the first row of elimination, and then the third row here is showing what's left after the third round of forward elimination. And then once you've completed forward elimination, we need to work backwards from x3 to x2 to x1, doing back substitutions to solve for the unknown. Here is some pseudocode that gives you the basic idea of what your code might look like when you implement Gaussian elimination. The basic idea is that you would have nested for loops that involve looping over each round and each row in forward elimination, and then substituting sequentially from looping from the last element to the next to the last, and so on. So so far, everything we've talked about has assumed that we could just go ahead and run Gaussian elimination the way that the algorithm is stated. But what happens if you have a 0 in this value? That would lead to a divide by 0 error. And so one of the approaches that we can do is called pivoting, where we change the order. We switch the order of the equations. And that's allowed because the order of the equations is not so important because these equations are independent from one another. And so what you do is you choose the row that has the largest first value and bring that to the top and use that as your new pivot column. Here's just an example of what that would look like and why that's important. On the left-hand side, I show a solution with the equations given as they are, and just kind of skip down to some key parts in here. Notice here we're dividing by a very low value that could lead to round-off error, and also down here when you're evaluating x1, we're dividing by a very small value, 3 times 10 to the minus 4. And so these sort of things could lead to round-off error and lead to error in our solutions. However, if you pivot, that means flip the order of the equations and put the 1 at the top, then notice here that all of these operations are kind of more on the same order as 1. And so we no longer have divided by very small numbers. And so you're less likely to encounter round-off error in your answer. So that's an example of why partial pivoting is helpful. Okay, so a couple of lectures ago, we talked about the rank of a matrix, and just to remind you, a rank is the number of linearly independent rows or columns of a matrix. And so, for example, in this A, that's a full rank. Its rank is 3 because each of these rows are independent from one another. However, in B, row 2 and row 3 are multiples of one another, and so that's not full rank. So that this concept of rank is quite important when we look at the types of solutions we might get when we solve for x in ax equals b linear system. So first, to remind you that the augmented matrix, augmented A, is A concatenated with B. And so first off, this is what we expect to happen, is that the two equations cross each other at one specific area. And we call this a determined system. And so that's when the rank of A equals the rank of the augmented A equals n. Okay, and so an example of this would be if it, x plus y equals 3, and x minus y equals 3. So they're just going to cross at one specific point. So that's the type of solutions we've been assuming so far. However, there are other situations that you might not have anticipated. First off is what happens if the lines don't cross at all, if there are no solutions. So that's called overdetermined. And that's when the rank of A is less than the rank of the augmented A. And so an example of that is x plus y equals 3 and x plus y equals 5. Notice there would just be a shift off of 1, and so there are no solutions that satisfy this. And then a third option, or a third possibility, is if there's an infinite number of solutions because the lines completely overlap. And so we call this an underdetermined system. Okay, and so that's when the rank of A equals augmented A, and it's less than n. Okay, and so an example of that would be if x plus y equals 3 and 2x plus 2y equals 6. You see that these are just multiples of each other. So these are two cases where there's not just one solution, and so both of these are called singular. Singular, because the determinant of A equals 0. So that's a hint to know that you're working with a singular system, where there's either going to be 0 solutions or an infinite number of solutions. And the final category of solutions is one where it's determined but just barely, that these lines are very similar to one another, and that's a case where that can be very susceptible to error. And so we'll talk about that in a little bit more, but the basic idea here is that if this is x plus y equals 3 and x plus 1.001y equals 3, the basic idea is that just a small amount of error could lead to a big change in the solution. Okay, so these are 4 different categories. So just because this is an important concept, just to reiterate this, is that in determined, you got a single solution. That's when the rank of A is the same as the augmented A. So that's a single solution. And then you can have cases that are overdetermined situations where there are no solutions, and underdetermined situations where there are an infinite number of solutions. And to figure out which one of these you've got, all you need to do is look at the rank of these matrices. Okay, so let's talk a little bit more about those ill-conditioned systems. So in a previous lecture, we talked about matrix norms, which gives us a way of saying how big a matrix is. And the condition number of a matrix is given by the norm of A multiplied by the norm of the inverse of A. And the reason why that's important for linear systems is that given by this equation right here, which says that the error in A is proportional to the error in the solution x, but multiplied by this condition number. And so if this condition number is really high, then that's going to lead to a large amount of error in our solution. So we have to be able to know how to look for this condition number and to understand what that does. So in Yeah, so as I just said, the relative error in X is proportional to the relative error in A times the condition number. And so if you've got a condition number that's quite high, then that's going to amplify round-off errors in your calculations. So that's why it's important to realize what this condition number is. So here's an extreme example of this, just to show you what can happen. So we have a system A and B, and if you calculate the condition number on this, you get 2503, which is much greater than 1. Okay, and so if we solve this system where x equals A inverse B, this is just another shorthand notation for A inverse B, then you would get, say, this result right here. However, if you would just change that A matrix just a little bit, call it this new C matrix, and just a little bit, at a 1,000th, and we see that the result is quite a lot different than what we had before. And so that's a result of the condition number leading to amplifying changes in these calculations. So another important concept is this idea of flops or floating point operations. And one of the ways in which you may have heard about flops before is that that's a way to that they quantify how fast like supercomputers can go, as how many flops it can compute at a given over a given time. And so for Gaussian elimination, the number of flops or operations needed to perform that is given on the order of 2 to the n cubed divided by 3 plus n squared, where this part is coming from the forward elimination, and this part is coming from the back substitution. Okay, and basically it's helpful to know that, like another, it's helpful to know when you're looking at an algorithm, like how the computational costs scale with the size of the problem. So for example, if you have a 10 by 10 matrix, so dimension 10, this is going to cost us 667 sort of operations, or little computational steps that the algorithm needs to take, on the order of this anyways. But if you scale up to 100 by 100, then you get over 600,000 operations that are needed. So basically, different algorithms are quantified by how the flops change with the size of the problem, and you can see that Gaussian elimination can get very costly because it's scaling with the cube of the size of the problem. Okay, and so the final concept we wanted to talk about in this lecture is this idea of matrix inversion. And so the basic idea here is that the inverse of the matrix is given by A times the inverse of the matrix equals I. And we're curious about whether we could solve for the inverse of the matrix by Gaussian elimination. I'll show you how that would work. So as we discussed before, the inverse of the matrix, the identity matrix, is just ones down the diagonal and zeros everywhere else. Okay, and so the way that we could solve for the inverse of the matrix by Gaussian elimination is to break it apart into pieces. Say A is a 3 by 3, then we could first solve a subproblem of this, which is the first column of the identity matrix, which is just 3 by 1. We solve for x. And then we could, so that would give us the first column of that would give us the first column of our inverse matrix. And then we would repeat this process with 0, 1, 0. And that would give us the y. And then we're going to repeat for 0, 0, 1, give us the z. So basically, what this shows you is that you can use Gaussian elimination not just to solve ax equals b problems, where x and b are vectors, but you can also efficiently solve for the inverse of a matrix. Okay, so to summarize the different concepts in this lecture, we reviewed Gaussian elimination and talked about how you eliminate variables through Forward elimination, use back substitution to solve for those variables or unknowns. But importantly, not everything goes according to plan, and so that's why in this lecture we've focused on some of the things that can go wrong, such as what happens if you've got zeros in your pivot coefficient, and we found that the solution to that is using pivoting, so you could swap the orders of the equations. We also talked about over and underdetermined systems, that we usually think about our systems as always being determined with one system, with one solution. However, if there is no solution, then that's what we call overdetermined. And if there's an infinite number of solutions, then that's called underdetermined. And so it's important to recognize when that's going to happen in a system that you're dealing with. And finally, we talked about condition number as a way of measuring how error is amplified when you're solving these linear systems. We find that in general, if you have a very high condition number, then you're very susceptible to making round-off errors in this solution. So thanks for watching, and I'll see you next time.